we have equal masses, okay? So unless it's really wonky, the target's always at rest, okay? I will never give you anything wonky where the target's moving. That's the target, it's just gonna be sitting. So these are gonna have the same masses. So this comes in, it hits this, it stops, this one takes off. So whatever momentum and kinetic energy this had is whatever kinetic energy and momentum this one has. This one stops, all of that energy gets transferred, which would be really weird because you couldn't hear it because you wouldn't lose any energy to sound, but that's not the point. Okay, scenario number 2. I'm going to have a really big target, excuse me, a really big bullet is going to hit a really small target, okay? So this is going to come in, boom, hit it. Now, as it rolls, what happens to the distance between the two carts? Why? Well, it's lighter.
So the acceleration makes it go
Oh, no, don't throw acceleration into this.
It's a bigger
off,
velocity.
takes it further.
Okay, so this is going to lose some momentum, right? This is going to lose some momentum in the collision. That momentum has to be gained by this. But this mass is small, so therefore the velocity has to be bigger, okay? Because whatever is lost here is what's gained here, okay? All right, now scenario number 2. I've got a small target, excuse me, a small bullet and a really big target. Now, with this one, when that hits, what happens? Changes direction. So mathematically, why that works is because when you do that subtraction of a small mass, and then you subtract a bigger mass from it, you get a negative value. So all that means is that this one is going to bounce back and go in the opposite direction. So is there a scenario dealing with however you want to arrange the masses where the target goes in the opposite direction of the bullet after the collision? Why? You shake your head no. Why?
Because there's not a force that can make it go the other way.
Yeah, because if it did go in that direction, what are you saying it's doing? Like, if you say it's going, it's like it's here, this is going to hit, and then they're both going to go like this, which makes no sense whatsoever, okay? It violates momentum, energy, Newton's third, I mean, you violated every possible law of physics that you can possibly violate at that point. Now, go old school momentum. So, equal masses. Roll this one in. Oh, hold on. That is not what I wanted to have happen. This is what I wanted to have happen. So that's a California problem. So could a California problem be a perfectly elastic collision? No. Okay? There's a couple of reasons. What do you know about the velocity of both of these after the collision?
Smaller than the original.
They're the same, right? Okay, because they're going to move off together. So mathematically, I can't generate in a perfectly elastic collision the same velocity. Okay? I can't do it. Now, the other thing that you'll see from an energy perspective, when these things collide, you actually lose typically about 50% of the kinetic energy in the collision. So if it's a California problem, okay, it cannot be a purely, where no energy is lost. Now, if I did this, if both of these were at rest, okay, and I let go like this, could that be a perfectly elastic collision? If you look at that math.
Yes.
If you look at that math, look at that new velocity, right? What's the initial velocity of everything?
0.
0. Okay? Everything is at 0. So mathematically that fails because of the fact that the initial velocity of the target and the bullet are both at 0. Okay? Got it? Good? Back we go.